Hi, everyone, and welcome to this next installment in my Algebra and Precalculus video series. In this video, I want to talk about properties of logarithms. Right? In the previous video, we defined the logarithmic function, the logarithmic expression, and what it means. In this video, I want to extend on that, talk about some properties of logarithms. Now, in this video, I'm going to talk about these 3 questions, or it's actually 9 questions, because we got 4 parts of number 1, 3 parts of number 2, 2 parts of number 3. So if you want to pause the video just for a moment, take a look at the problems I'm going to be doing later. Now, but before we can get to any of these, we have to first discuss some properties of logarithms. Right? So to talk about properties of logarithms, we got to talk about the definition of the logarithm. Now, this was the topic of the previous video. And this is an implicit definition, meaning we don't define the logarithm in and of itself, but we define it in terms of how to translate back and forth from exponential form to logarithmic form. Okay, we can go back and forth. This definition goes both ways. So this is like it's working. For example, just like Google Translate, right? You put in one language and the translator spits out another language, right? Same thing. So what we're going to do is we're going to start with this list of properties of exponents, right? This is something that at this point, hopefully we're familiar with, right? Properties of exponents. So what we're going to do is we're going to apply the definition of the logarithm to each one. Boom, 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 and translate from exponential form to logarithmic form, right? And so we're just taking, we're not generating a new list of properties. We're taking a list that we've seen in the past of exponents and just rewriting or translating each one of these into logarithmic form. So the first one, when you multiply like bases, you add the exponent. X to the third times x to the second is x to the fifth. Now, this we've seen before. Now, in the language of logarithms, remember the logarithm is the exponent. Right? So the log base b, where b could be anything. Right? I say base b, it could be common log, natural log, log base 3, log base 14, log base 109. The base doesn't matter, right? Any base. So the log of a product is equal to the sum of the individual logarithms. So the log base b of x times y can be rewritten as the log base b of x plus the log base b of y. Okay, next rule of exponents. When you divide like bases, you subtract the exponents. Now, in the language of logarithms, the log of a fraction or the log of a quotient is equal to the difference of the logarithms. Right? Next rule of exponents. When you have a power raised to another power, b to the power of x, and then that's raised to the power of y, we multiply the exponents. X to the second raised to the power of 4 is x to the 8th power. All right. In log form, this becomes exponent to an exponent goes to multiplication. So the log base b of x to the c is equal to c times the log base b of x. So what that looks like, if you have the log of x to the third power. That is equal to 3 times the log of x. 3 times the log of x. So what happens is the exponent pops out front as a multiple. The 3 pops out front, you get 3 times the log of x. In the next section, in the next video after this one, we're going to actually use these rules, right? So if you think about the analogy of doing math like it's going and building something, going to a construction site, this video is like going to Home Depot, buying a bunch of tools, right? In the next video, we show up at the job site and we start building things. But these are our tools, right? These guys right here, these are our tools, these properties. So first we have to establish our toolbox, then we could start using them. And when we start using them, I think they're going to start making more sense. Okay, next one. And these 3 are more like, this is one rule. Basically, the first 2 are just sort of special cases of this rule, but we know from our knowledge of exponents, any number raised to the 0 power is equal to 1. So in log form, this is saying when you take the log of 1, you get 0. Log of 1, so any base, log base b of 1. And you take the log of 1, you get 0. And that's because, I mean, we're just literally translating using the definition of a logarithm, exponential rule to logarithmic rule. Okay. We know that any number raised to the first power is equal to itself. So in the language of logarithms, the log base b of b, right, when you take the log of something where the argument and the base are the same, you get 1. Right? And this is just a new way of saying something we already know. Any number to the first power is equal to 1. And the next rule is it's not even really a rule. It's just stating the obvious. B to the x equals b to the x. Maybe it's a little more visually apparent what's going on here if I say in parentheses b to the power of x is equal to b to the x. But when we put this in log form, b to the x is equal to b to the x. Okay, so when the base and the argument are the same number, like what would be the log base 3 of 3 to the 9th power? Well, according to this property, it would be 9. Log base 3 of 3 to the 9th should be 9. Another way of looking at this is that the logarithmic part and the exponential part are inverses of each other. So they cancel each other out. Now, what we're going to do, at least for the remainder of this video, and also into the next when we're talking about solving various types of equations, we're going to take one big complicated logarithm and split it up into smaller pieces. Right? Sometimes that is helpful. Sometimes that gets us to a point where we're able to do something that we want to do. And sometimes we're going to start with a bunch of simpler pieces, simpler logs. I'm being very, very informal in my notation here. And we're going to combine them into one more complicated logarithm. Sometimes it makes things easier when you've got a bunch of simple logarithmic expressions. Sometimes it makes things simpler when you have a single logarithmic expression. Doesn't matter if it's more complicated, having just one is more ideal. We'll talk about different situations where each of these apply, but that'll be the next video. Before we can talk about, how to apply that, we have to talk about how it works first. How can we split one log up? How can we combine multiple logs into one? Okay, so what we're going to do is take this list of logarithms, and again, this is our toolbox. This is our toolbox for logarithms. By the end of this video, I think we're going to add maybe one more to this list. Maybe one more. But this is most of them. All right, so let's do some problems. So for each of the problems in the remaining slides, I've got the properties of logarithms copied in. So we're able to just reference visually which ones apply. Okay, so we use the properties of logarithms to expand the logarithmic expression as much as possible. Okay, so we want to take this, the natural log of e squared over 13, and break it up as much as possible. Okay, so if you look over here on the right, our list of log rules, well, which ones apply? Well, I see a fraction, so probably the fraction rule is going to apply. And I also see an exponent, so it seems like that one's going to apply as well. It's important we're doing things in the right order. So it turns out in this problem, we have to start here. We have to start with the fraction rule. And the reason why, this exponent rule doesn't apply to the whole argument. It only applies to the top of the fraction. So it's all or nothing. It's all or nothing. Either the rule applies to the entire expression or it doesn't apply. So we can't start with the exponent rule because this exponent, the second power, doesn't apply to the 13. Right? So we're going to start with the quotient rule. So the natural log of a fraction, or any log, this is log, remember, natural log of x is the same, what it means is log base e of x, right? This is what we write though. But this is what it means. Okay, so natural log, let's get rid of this for now. Natural log of a fraction is equal to, nothing special about natural log in this case. It could be any log, log base 2, log base 10, log base 3. In this case, it's natural log. So natural log of the top minus the natural log of the bottom. Natural log of the e to the x minus the natural log of 13. All right, now it looks like now we're at a point where we could apply the exponent rule just to this part. Just to this part. So the exponent rule says when you have the natural log of something to a power, the power pops out front. This becomes 2 times the natural log of e minus the natural log of 13. Now we could actually apply this rule now. Okay? Same reason. What I said earlier, ln, when you see ln, that means the natural, or sorry, that means the log base e. ln stands for natural log, and what it means is the log base e. Not equal, that's minus ln 13. All right, so this is what we write. This is what we mean. And now this rule applies. When the base and the argument are the same, this in the red box is equal to 1. Is equal to 1. This becomes 2 times 1, or just 2, minus the natural log of 13. All right. This is the kind of thing, once you do a dozen problems, 10, 12, 15 problems, then it starts becoming more clear, more comfortable. But there's this, I can't do one problem, then make it, everyone be at a point where you're 100% comfortable with these types of problems. All right, next one. The log of the 14th root of x. The log of the 14th root of x. Well, it's hard to see, maybe it's not, but maybe it is hard to see that this is the property we're using. We have the log of x to a power. Right? We have the log of x to a power. Because the 14th root of x is the same as x to the power of 1 over 14. I actually talked about this in the video right before this one. Square root of x is x to the 1/2 power. The third root of x is x to the 1/3 power. The fourth root of x is x to the 1/4 power, and so on. So x to the 14th root of x would be x to the 1/14 power. Right, so the nth root of x is equal to x to the power 1 over n. Right, it's another rule of exponents. This is not, part of the current topic, but this is something we need to pull in from the past. When you have the log of an exponential expression, the exponent pops out front as a multiple, so that's 1 over 14 times the log of x. Or another way we could write this, not any more correct, but equally correct, would be the log of x over 14. Either way works. All right, let's do another. The log base b of x to the second times y times z to the 7th power. Well, I'm seeing a multiplication right here. I'm seeing a fraction right here. Okay. I'm seeing exponents here and here. Well, it looks like at least those first 3 rules are going to apply. Only one of them works. Only one of these 3 works as our first step. Okay, so let's go down the list. First one, multiplication. Multiplication only applies to these 2. It doesn't apply to the z. That doesn't work. The exponent rule. Well, for the 2, that only applies to the x. The 7 only applies to the z. Nothing applies to the y. But the fraction rule, this is the top of the fraction, numerator. This is the bottom of the fraction. This applies to the whole argument. All right, so it looks like we got to start with the quotient or the fraction division rule. All right, so this is the log of the top, so log base b of x squared y minus the log base b of z to the 7th power. Now, do we use the multiplication rule or the exponent rule next? Well, the exponent rule, this exponent doesn't affect the y, it only affects the x. Right? All or nothing. It either affects the entire argument or it doesn't apply at all. So that one doesn't work. But it looks like the multiplication rule. Looks like the multiplication rule we could apply. So that's the log base b of the first factor, x squared, plus the log base b of the second, which is y. All right, so we're splitting that up into two terms, okay? We still got this, don't forget, we still got the minus log base b of z to the 7th power. Well, now it looks like we could apply the exponent rule. This exponent will pop out front. This exponent, the 2, will also pop out front. So we've got 2 times the log base b of x. Now you could use parentheses if you want. You don't need them. You're not wrong if you put them. Either way. Plus the log base b of y minus 7 times the log base b of z. And I think that does it. We're deconstructing, we're decomposing, we're splitting this up. This initial single logarithm, we're splitting it up into its smallest, most basic pieces. Okay, one more. The log of the cube root of x over y. So definitely, as soon as you see a root, in this case, it's the third root, the cube root. As soon as you see a root, rewrite it. So that's x over y to the power of 1/3. X over y to the power of 1/3. So it looks like here we could start with the exponent rule because this exponent applies to the whole fraction. So this exponent pops out front. So that's 1/3 times 1/3 times the log of x over y. All right, so now it looks like we have the fraction rule applies here. So this would be 1/3 times the log of x minus the log of y. Now you have to be careful here. This doesn't look right. This doesn't look right to me. So in the second step, this 1/3 was multiplying by this entire log, right? Which means in the next step, this 1/3 has to multiply by everything. So we got to throw in some parentheses here to make sure each step is equal to the step before it. All right, so this looks good. Now, In these first four problems, we went from complicated to simple. Now we're going to go in the other direction. Use the properties of logarithms to condense the logarithmic expressions. Right? So we want the final answer to be a single log. In this case, natural log, but regardless of the original base, the log of something, one single logarithm. All right, so problems that say condense, this is what we're looking for. All right. This one looks like it's just one step. It looks like we have the right-hand side of this first rule. So we could write this as the natural log of x times 20, or 20x. And for this one, this is as far as we go. We usually do green. There we go. Green circle for the answer. Yeah, so this is as far as we go in this one. The next one, we got the log of y plus 6 times the log of z. We have a rule for addition, but if you look at the rule, there's no number in front of the log, right? It's a single log, 1 log b of x, 1 log b of y, right? So we can't apply this rule because of that 6. Right? So we can't do that. Let's get rid of all of this, but it looks like we can apply this rule here. The multiple out front goes up. If you start with log base, or the log of z to the 6th, you could put the 6 out front. It goes both ways. So if you have an exponent, you could put it out front. If you have a multiple out front, you could bring it up as an exponent. Depends on the problem. Depends on what you want to do. In this case, we're trying to condense the logarithms. So we'll take the 6, bring it up top. So that's the log of y plus the log of z to the 6th power. Now we have a single logarithm plus a single logarithm. So now we can apply this guy. So first we started with this. Now we've got this. So this will be the log of y times z to the 6th power. Y times z to the 6th power. And I think that's as far as we can go with this one. Okay, so that's it. Take one log, split it apart into smaller pieces, or start with smaller pieces, combine them into one log. Let's do one more of these. Well, we got 2 times the natural log of x plus 1/2 times the natural log of y minus 3 times the natural log of z. Well, we definitely have an addition, right? We have an addition right here. We definitely have a subtraction. We've got a subtraction right here, but we can't apply either of those rules. Both of those don't work because we have these multiples out front. Right? These rules have no multiples out front. The log of x plus the log of y. The log of x minus the log of y. There's no 2 log of x. There's no 1/2 log of y. It's just log x and log y. So what we can do is, we're going to apply those, but first we can apply this guy. The exponent rule. The 2 comes up top as a power. The 1/2 comes up top as a power, and the 3 comes up top as a power. So that will be the natural log of x to the second plus the natural log of y to the 1/2 minus 3. Oh no, 3 is coming up top. Minus the natural log of z to the third power. And now we've got addition, subtraction, and I tend to go just left to right, addition first because it's the first one on the left, and then subtraction. So we'll go 2 and 3. It doesn't matter. You can go subtraction first, then addition. You're going to get the same answer. But if we combine those two with addition, that's going to be the natural log of, we still got a minus natural log of z to the third. So the natural log of x to the second plus the natural log of y to the half. So that would be natural log of x to the second times y to the half. And now we've got a subtraction. All right, so we could apply the second one on the list. Ooh, the one I have labeled as the third, because that's the third step. And you have a log minus a log. In this case, it's the natural log, but any log. When you have subtraction, it condenses to the log of the first over the second. First argument over second argument over z to the third power. And that's going to do it for this one. All right, looks good. Looks good. So let's just add one more. We've got 6 rules over here on the right in the green box. Let's just add one more rule to that, which we're going to need for the last problem I want to cover today. So I want to move on to the next slide. Use either the common logarithms or the natural logarithms to evaluate the following expression. Round the answer to 4 decimal places when necessary. All right. So look at this guy down here. Forget about this for now. We'll talk about that in a minute. Right? Look at the problem. This is log base 9 of 23. Log base 9 of 23. In my last video, I talked about these 2 special bases, right? Log base b of x. These two special values for b, the common logarithm where b is equal to 10, and the natural logarithm where b is equal to e. So let me bring over my calculator here. All right, so if you look at the left-hand side of the calculator, next to the 7 and the 4 and the 1, just to the left of the 7 and the 4 key, you'll see a button for LOG. And you'll see a button for LN. Right? LOG is the common log, log base 10. And LN is the natural log, log base E. So you've got a button for log base 10. You got a button for log base E. Because those are the 2 most important. Probably log base 2 would be the next most important, but the in terms of mathematics in general, the common log or the log base 10, the natural log, which is the log base E, those are the 2 more important ones, just because we use them more often, much more often. Enough so that each gets its own button on a calculator. So some people some books refer to these two collectively common log and natural log. Right? It's plenty of people refer to these two collectively as the calculator logs, because most calculators have a button for each one. There's no calculator with a log base 9 button. Right? We want to do in this this problem down here, the log base 9 of 23. There's no log base 9 button. But what we can do is change the log base 9 into one of those calculator logs. And for that, we use this, what's called the change of base formula. Well, it's a little more complicated, in terms of its statement than it needs to be. But what the change of base formula is saying there we go. What the change of base formula is saying is when you want to do this, right? This is what you want. Like down here, the log base 9 of 23. You could rewrite that as any other base. So notice there's a C on the right-hand side, a C here and a C here. C can be anything. We could change log base 9 into log base 6, or we could change log base 9 into log base 11, or log base 44, but none of them will help us. But what we can do is change log base 9 into one of the two bases that appear on the calculator, either 10 or E. So here's what the change of base formula is saying. The log base 9 of 23 is equal to the log base 10 of 23 divided by the log base 10 of 9. Right? This number goes on the top, a little number goes on the bottom. Now that's not the final answer. We got to figure it out. We got to round to 4 decimal places. We got to still crank out a number. But we could also, if you don't want to use the common log, we could also alternatively say the log base 9 of 23 is the log base E of 23 over the log base E of 9. Same thing. Big number goes on top, little number goes on the bottom. Use any base you want. Okay. So let's see. The log of 23. That's about 1.361 something, something, something. Well, the natural log of 23, that's a completely different number. But when you divide these two fractions, so the one on top, the log 23 over log 9, let's type that in. The log 23 divided by the log of 9. All right, so that would be the answer to the problem. Or if you did it a different way, if you use the natural log, so it would be the natural log of 23 divided by the natural log of 9. Those are two different numbers, but we get the exact same answer. All right, so the log base 9 of 23, there is no log base 9 button. So we convert the log base 9 into a different log where there is a button on the calculator. And you got two options because you got two log buttons. There's the common log and there's the natural log. All right, so that's the change of base formula. Change of base formula, for at least for this class, is going to be only for situations where we have to get an exact answer from a calculator. And it's not a base 10 or base E, some other base, like base 9. One more problem. Let's do another one. The log base 15 of 88. All right, you got two options here. It's a really quick problem without all of my explanation and my lecturing. But the log base 15 of 88.5, you could either do the log of 88.5 over the log of 15. That'll give you the answer. Or you could do the natural log of 88.5 divided by the natural log of 15. And that will give you the answer. Same answer. You don't have to do both. It's one or the other. So let's just test it out just to verify the log of 88.5 divided by the log, that's common log, of 15. Okay, there's an answer. Or we use natural log. Natural log of 88.5 divided by, let me close those parentheses, divided by the natural log 15. We should get the same. Yep, there it is. And we're rounding to 4 decimal places, so it looks like 1.6554. 1.6554. So it doesn't matter if you're using the common log or the natural log. Either one works. All right. That does it for this video. Next video, we're going to continue on with logarithms. And we're going to take everything we talked about in this video, maybe except the change of base formula, but all the other properties, those other 6 properties that were on the previous slides, we're going to take those and apply them to solving equations that involve logarithms. All right, so it's not just, let me go back a slide or two so we can see the list. Okay, so this list here, I would include the definition as well. So you've got 1, 2, 3, 4, 5, 6 properties here. Plus you've got the definition of the logarithm. That's going to be important in terms of solving equations. And also this idea that they're inverses. Exponential and logarithmic functions are inverses. All right, but that'll be the next video. That's it for now. I hope this was helpful.